Okay, so today I want to talk to you about Vesper. It looks like it's misspelled, Vesepr, Vesper, but it's not. It stands for something, valence shell electron pair repulsion, and you'll hear some people pronounce it differently, but that's okay. So I'm going to show you this TED Ed video because you know how much I love TED Ed. And I think that it does a great job of describing Vesper to you, and it shows you the shapes. Okay, so Vesper is all about shapes and it's all about three-dimensional shapes. So try to work your brain in a three-dimensional world right now. It's actually called What is the Shape of a Molecule?
What is the shape of a molecule? Well, a molecule is mostly empty space. Almost all of its mass is concentrated in the extremely dense nuclei of its atoms. And its electrons, which determine how the atoms are bonded to each other, are more like clouds of negative charge than individual discrete particles. So a molecule doesn't have a shape in the same way that, for example, a statue has a shape. But for every molecule, there's at least one way to arrange the nuclei and electrons so as to maximize the attraction of opposite charges and minimize the repulsion of like charges. Now let's assume that the only electrons that matter to a molecule's shape are the outermost ones from each participating atom. And let's also assume that the electron clouds in between atoms, in other words, a molecule's bonds, are shaped kind of like sausages. Remember that nuclei are positively charged and electrons are negatively charged, and if all of a molecule's nuclei were bunched up together, or all of its electrons were bunched up together, they would just repel each other and fly apart, and that doesn't help anyone. In 1776, Alessandro Volta, decades before he would eventually invent batteries, discovered methane. Now, the chemical formula of methane is CH4. And this formula tells us that every molecule of methane is made up of one carbon and four hydrogen atoms. But it doesn't tell us what's bonded to what, or how the atoms are arranged in 3D space. From their electronic configurations, we know that carbon can bond with up to four other atoms, and that each hydrogen can only bond with one other atom. So, we can guess that the carbon should be the central atom, bonded to all the hydrogens. Now, each bond represents the sharing of two electrons, and we draw each shared pair of electrons as a line. So now we have a flat representation of this molecule. But how would it look in 3 dimensions? We can reasonably say that because each of these bonds is a region of negative electric charge and like charges repel each other, the most favorable configuration of atoms would maximize the distance between bonds. And to get all the bonds as far away from each other as possible, the optimal shape is this. This is called a tetrahedron. Now, depending on the different atoms involved, you can actually get lots of different shapes. Ammonia, or NH3, is shaped like a pyramid. Carbon dioxide, or CO2, is a straight line. Water, H2O, is bent like your elbow would be bent. And chlorine trifluoride, or ClF3, is shaped like the letter T. Remember that what we've been doing here is expanding on our model of atoms and electrons to build up to 3D shapes. We'd have to do experiments to figure out if these molecules actually do have the shapes we predict. Spoiler alert, most of them do, but some of them don't. Now, shapes get more complicated as you increase the number of atoms. All the examples we just talked about had one obviously central atom, but most molecules, from relatively small pharmaceuticals all the way up to long polymers like DNA or proteins, don't. The key thing to remember is that bonded atoms will arrange themselves to maximize the attraction between opposite charges and minimize the repulsion between like charges. Some molecules even have 2 or more stable arrangements of atoms, and we can actually get really cool chemistry from the switches between those configurations. Even when the composition of that molecule, that's to say the number and identity of its atoms, has not changed at all.
So, as we start to look at Vesper, I want you to keep all of those shapes in mind and why they're happening, why things are pushing down in the direction they are. So that's what Vesper stands for, valence shell electron pair repulsion. It just means that the electrons repel each other as much as they possibly can. It says that orbitals try to spread apart as much as possible. And the electron orbitals, remember, are like clouds that are surrounding the nucleus. I've got uh, 6 shapes I'm going to teach you. There are more that you can learn, but I've got the basic 6 shapes that we have to go through. So you need to know all 6 of these shapes. And the way that I like to organize them is by electron domains or things around the center of the atom. So the first one is called a tetrahedral. If all 4 orbitals are bonding and there are 0 lone pairs, we call this a tetrahedral shape. It's probably the most important shape in all of chemistry because carbon, which makes up everything, loves to bond in tetrahedral shapes. Couple things about the tetrahedral. It's very even in all 4 directions or in 3-dimensional. Another thing is that the bond angles between the atoms are 109 degrees. So these bond angles here between each one of those are 109. Now, I don't care if you say 109.5 or less than 109. We can get very nitpicky with this, but I say about 109. All right, now I want you to imagine that I'm holding that right now, and then I take one of these atoms and I pull it off, okay? And I replace it with a lone pair. That's called a pyramid shape or a pyramidal or trigonal pyramidal. It also has a bond angle of 109 degrees. And the only thing that makes it different is that it has lone pairs kind of up at the top there. They'd be floating, but I can't make them 3D float. All right, so now if I took that molecule and I took off another atom, I would get the last shape here, and it's called bent. Bent means you have 2 things bonded, and then you have 2 sets of lone pairs that are kind of pushing those down. So let's take a look at the molecules we have here. We've got CH4, which is methane, tetrahedral shape, NH3, which is ammonia, gives me a pyramid shape, and then H2O, which is water, gives me that bent shape. Non-polar, polar, and polar. As soon as I have lone pairs on the central atom, it becomes polar. So now let's go down to 3 electron domains. If I have all 3 electron domains and it's bonded to all 3 things, we call this trigonal planar. Okay? It's a triangle and it's all on one plane. The bond angle is about 120 degrees now because we only have 3 things around it. I want to note here, it doesn't matter whether the bonds are double bonds or even triple bonds or single bonds. That doesn't matter at this point, and you'll learn more about those in the future. But this happens to be BH3, which is all single bonds. But we often see trigonal planar shapes with 1 double bond and 2 single bonds. If I were to take one of these atoms and pluck it off, I would have a lone pair and I would get another bent. It's like a different kind of bent. And this is different because it's bent at 120 degrees instead of bent at 109 degrees. And the reason it's 120 is because, and I can't draw because it's 3D, it only has 1 lone pair instead of like water that has 2 lone pairs. It doesn't matter really too much. Bent is still going to be bent. It just kind of affects the angle. And the last one I want to tell you about is if you have just 2 electron domains, and that's going to be linear. It doesn't matter if there's a lone pair there or not. If there's a lone pair, then you've got only 2 things, which means you're still in a line. So linear is linear, and it has a bond angle of 180, which is, I guess, to be expected if you've got something that's linear. If you look here, I don't show you this to scare you. I show you this to like let you know. Here's where we are in Chem 1, in basic chemistry. We do those 6 shapes, okay? Sorry, I feel like I like drew over those. So we've got the tetrahedral, the trigonal planar, the bent, another kind of bent, linear, and trigonal planar. When you get to AP, you would do all the rest of these shapes. We don't do these shapes because they involve exceptions and we don't talk about exceptions. So these are the only shapes we do. A couple things I want you to notice about the way that this chart is set up. Its chart is set up with a number of domains. Look, it's bonded 4 times, tetrahedral. It's bonded to 4 things. It still has a tetrahedral shape around it. The difference is that one of those is a non-bonded pair or a lone pair. Same thing, it's bonded 4 times, but 2 of them are lone pairs, right? So that's where this 4 comes from. How many times is it bonded? All 3 of those all have about 109-degree bond angles, and all 3 of those have a tetrahedron shape electron geometry. And that's a little bit tricky, but I'll show you some examples of that. This one right here, trigonal planar and bent, same thing. And then here's linear. And like I said, if you look down at the bottom there, there's some of the ones that you would do if you went on in chemistry. I love the name of the sawhorse or the seesaw, and you've got square planar and T-shaped like you talked about in the video. But we don't do any of those in this class. So take a look at these, and in your head right now, using your brain in your notes or whatever, see if you can figure out what the shapes are before I reveal what the shapes are, okay? So see if you could look at those and tell me what shape it is. There's a couple clues as far as bond angles. This first one has just 2 things in a row here. So of course that's linear. This one has 3 bonds. It's bonded to 3 things. So I'm down to like trigonal planar or pyramidal, but the 120-degree bond angle gives me a clue there that I've got trigonal planar. Also, it appears again to be on all one plane. This one is my favorite shape, my famous shape in all of chemistry, the tetrahedral shape, right? This is bent. I don't know if that's bent at 109 or bent at 120. In other words, I don't know if there's 1 lone pair up here or 2 lone pairs up here. Quite frankly, I guess I don't care for this example, but either way, it's bent. And then this one, it's hard to see, but it is pushed down. There is some sort of lone pair pushing that down. That is a trigonal pyramidal or a pyramid shape. Sometimes they throw the word trigonal in front of it. Sometimes they don't. Sometimes they just call it a pyramid. It's okay. It's all kind of the same thing. So those are the shapes. So then you can take those shapes and bring that back to polarity. So this says determine if the following molecules are polar and non-polar. Well, if I've got 2 H's, like I do in this example, this is a linear shape. It's bonded to the same thing. It has absolutely perfect symmetry. So that example is non-polar. Below it, I have NH3, ammonia. I keep giving you the same examples on purpose so you can really get familiar with these molecules. Up at the top here, I've got a lone pair. That lone pair tells me that it's pushing these down. So this one automatically is polar. Now, like you said in the video, molecules aren't always tiny like this. In fact, this is a great example. Ammonia is a great example. In organic chemistry, we have something called amines and amides. And it means that there's this little portion of the molecule at the end of big long carbon chains and big long carbon circles and stuff like that. And this is a really important part of pharmaceuticals and is the reason that some drugs work the way they do. Actually, legal and illegal have these amines and amides. And it's because of this polarity that they start to act the way that they do. And then the last one here is CH4. It's a tetrahedral shape. It's bonded to the same thing 4 times, and it is non-polar. Okay.